Graphene is a unique nanoscale form of carbon that is disrupting legacy materials, bringing step-change improvements in performance across a wide range of industrial and consumer applications. From energy storage and electronics to everyday materials, graphene enables products that are better, stronger, and lighter, while increasing durability and improving sustainability. Graphene is leading the era of new advanced materials.
The following is a presentation that was given as part of a two-day virtual Graphene Investors Conference, hosted by the Graphene Council.
Hi everybody, my name is Stephen Fairclough. I'm the co-founder and CEO of GSC Nanopore. We're a spin-out of Groltex, the company that was listed on the program here. We're on a mission to decode all biological information by digitizing sequencing using our graphene-based sequencing technology. And we're going to be starting with protein. So if you go to the next slide, I appreciate it. So at this point, everybody's familiar with the revolution that DNA sequencing has had on understanding the blueprint of life. This was brought into the cultural zeitgeist in 2001 with the publication of the Human Genome, and has become the primary way that biologists have interrogated biology for the last several decades. Currently, we sequence the equivalent of 9.4 million whole human genomes per year, and this is expected to grow by 17.6% for the next decade. If you go to the next slide, please. If you're familiar with the space, you'll know that Illumina, an optics-based sequencing company, has really captured this market. They have a $20 billion market cap, 80% market share, and their sequencing by synthesis methodology is well suited to sequencing template-based biological molecules such as DNA. However, their approach has some limitations. Most of what's interesting about biology exists outside of the DNA, right? Anybody who's interacted with a blueprint knows that touching or seeing the actual thing is an entirely different experience. And proteins are the machines of life. These are the things that actually carry out the biology in cells. And currently we don't have a technology that allows us to sequence single molecule proteins in a high throughput fashion. So much of what's interesting about biology actually lies outside of what we can see. So in 10 years, not only will the demand for sequencing be more, the diversity of what we'll be trying to sequence will be more. And we don't have a technology that can allow us to capture that increased molecular diversity and molecular activity. So an emerging technology that's being explored to achieve this is what's called nanopore sequencing. So to put us all on the same page, I'll give you a quick primer on nanopore sequencing. A nanopore is basically a hole in a membrane, and ions are flowed through that hole to create an electrical current that people can measure. And when a molecule passes through that hole, it disrupts the ionic flow, and you can measure that disruption in an electronic signal. The problem with this simple design is that the molecule wants to travel very quickly through that hole. And so if you're trying to measure individual monomers in this polymer, it moves too fast to make those measurements. So the way that the field has attacked this is by controlling that translocation speed by putting proteins. And they use these proteins to control that translocation process. Now, there are three challenges with this. First is the proteins are specific, so they immediately eliminate most of the molecules that you can sequence. So this is really suited for DNA sequencing technology. The second thing is that if you look inside that red square, you'll see that there isn't a single monomer in there. There's actually 5 or 6 monomers, and we're trying to get to monomer level accuracy. So there's an inherent limitation in the accuracy of what we're trying to do here. And then finally, the proteins themselves don't integrate well into the rest of the system and have high failure rates. So the scalability of this is fairly limited. So quickly to summarize, the existing technology of biological nanopores are inherently limited in the types of molecules they can sequence, their fundamental accuracy, and their ability to scale. So an alternative to biological nanopores are what's known as solid-state nanopores. Solid-state nanopores can work with any type of molecule. Their pore depth can be tuned for accuracy. And the way we do it, we use semiconductor fabrication that scales easily, as proven in the computers that we're all on or in your phones that are in your pocket. This is well-worn technology. What enables this design is actually the graphene electrodes that we're able to build into these heterostructures and expose on the edge of that pore that I showed you. So we were able to build graphene in single atom thick layers here. And if you look here, you can see now we can build at the appropriate resolution, right? So we can build at the level of the monomer that we're trying to measure. So because these are graphene, we're able to send electrical charge through these. This allows us to engage the molecule as it passes through. That charge effectively grabs on and allows us to control the translocation of that molecule, which was the first fundamental challenge that we were trying to solve for. And because we can do this electronically now, we can control the rate and direction of the molecular movement. Once we're engaged with the molecule, again, because we're passing current through this set of graphene electrodes, we can now measure the resistance or quantum tunneling through that to generate an electronic signature to allow us to decode monomers as they pass by. And because we can build these heterostructures in stacks in any configuration that we'd like, we can put in as many electrodes as we like to enable multiple measurements on a single pass across the molecule for superior accuracy. So we're able to build this because of our foundry down in San Diego, Groltex, who can build these graphene and HBN in sheets of high quality and then build the resulting heterostructures in the configurations that we need. And they can currently produce 1 million chips per shift. And this is all protected by sort of IP and trade secrets. And it's not just the fabrication themselves, the fabrication that scales, the actual production of what's called the flow cell or the unit cell that would be used for sequencing, because we're using semiconductor approaches, actually scales to much higher densities than the current technology, 1 to 2 orders of magnitude higher density. And because we don't have proteins in there, because we're using graphene as an electrode, and this is a solid state thing, the failure rate is much lower, and we expect a much higher yield, which will ultimately increase the throughput of the whole device. So we're currently doing a seed round of funding, targeting between 625 and 800K on a $10 million post-money valuation. We're going to be using these funds to demonstrate electronic control and the quantum tunneling that I told you about today, and we're targeting a close of July 1st. So I'm happy to answer any questions that people might have right now or dialogue with anybody. Alternatively, if you want to get our materials from Terrence later or reach out to me via my email listed here, I'm happy to follow up with anybody. Thank you.
Fantastic. Thank you, Steve. Let me do this. We'll distribute your slides. So first of all, thank you for sharing that, because I feel like I've learned something today, and I was super fascinated with the fact that you're also using HBN in there. And for those of there may be folks on this call, they're familiar with what graphene is. HBN is hexagonal boron nitride, which is another 2D material, which is, I would say, at a maturity level at par with graphene. And it was encouraging to see you guys using that in that sandwich, in that heterostructure. I think that's brilliant. And you're also, I'm not an expert in this, but when you say that you're looking at proteins, that indeed is right. What translates all of it's the machinery of life, right? It actually executes. And how many proteins are there?
So at a certain level, we don't know, right? This is actually we'll be able to uncover new biology with this technology, right? We haven't had a way to characterize the proteome. So we started off sequencing DNA, but there isn't a one-to-one correspondence. There are actually changes that happen along the way. As you move from DNA, it gets transcribed into RNA, and there are multiple transcripts that are made. That's part of the way life regulates the biology. And then even from that RNA, turning it into protein. And we've had devices to characterize the DNA that I told you about. We've done some funny molecular biology to understand that RNA, but we don't really have a technology that enables us to understand the end product, the protein. Most of this is done on average in aggregate. And anybody who's looked at human diversity knows that looking at humans in aggregate it tells you stuff, but it doesn't tell you about the individuals, right? And that's what we want to try and uncover with the protein space, right? So to really be able to look at individuals. And I can tell you, some of my colleagues, my scientist colleagues are very excited about this technology.
Excellent. And I'll ask another question before we sign off here today, regarding the business model. Okay, so you're moving now to prove out the efficacy of this approach. Is your intent then to actually manufacture devices, manufacture systems, license the technology? What do you? Obviously that can change as you go forward and see what the market reaction is. But what is the theory?
Yeah. So I think all of the things that you said, obviously, part of this involves making the market, and that's why we're involved with early adopters in the research space. I think an early application would be people who are doing sort of mass spec or protein mass spec would find this particularly useful. And that would really start to prove out the technology. And this was sort of the approach that Illumina took is once you build out into sort of a known market, you start to expand on top of that. The way that I view this is sort of building the platform. And then one of my partners and I have actually spent the last 2 decades building applications on top of DNA sequencing. And that can happen either directly or through licensing in the protein space.
Excellent. Thank you very much. Really appreciate your presentation. And Groltex has been a long-standing member of the Graphene Council. We're very happy to see the progress. And I think this is, it's also very exciting to show what graphene can do at that true, single atomic layer, what the difference is in one of the really exciting areas. We haven't seen that many presentations on it, but having graphene in the life sciences, in the diagnostic space is one of the great opportunities, I think, for this material.
For more information on market opportunities and to connect with experts, contact the Graphene Council at thegaphenecouncil.org.